Hello and welcome to IGB381 Game Engine Technology Procedural Texturing. This is my favorite lecture because I think this is the most fun part of the unit where you get to do some really interesting stuff with noise and how that can be used to generate physical phenomena. So today, just an introduction to the ideas of procedural generation, including other more deterministic models, and the mathematical bases, noise, what is it good for, procedural texture examples, where I cover some natural phenomena that you can, some entry-level natural phenomena approaches you can do with game engines. I noticed this here again, just to reiterate for those who are working away on your assignments. Have a look at this video, see some information where I cover how to use various variables, putting them out as colors and so forth inside of shaders. Yes, it's archaic. This is like doing Kernighan and Ritchie C in the 80s with printf statements. But hey, that's life, and sometimes in Unity I don't use the debugger, I just use debug.log because hey, it's quick. So similar thing here. Keep this in mind, especially when you get weird phenomena occurring, including objects disappearing, as I show you in some other videos. This is just a good thing to get into. Procedural content. So everything you've been using so far has been generated by a human using a tool, or maybe you're just using basic shapes that are generated in Unity. Funnily enough, those little basic shapes are a form of procedural content generation. Some of them will be generated by scripts. Some of them will maybe be stored somewhere. I actually haven't had a look. It's worth diving into Unity and finding out where those objects come from, one of those things. But most of the stuff you've been using in your games is some poor benighted artist sitting there by candlelight in their atelier, or artist garret, whichever language you want to use, and they've been generating this stuff. That's great. That enables you to have, these configurable environments and virtual worlds and games and experiences. But that's not the only way to generate visual phenomena in 3D. And in particular as well, not only just the structure of 3D objects, but the textures that are on them, which sort of interests me mostly because I cover the surface representations in this unit. They're generated from people painting, people using Wacom tablets and so forth. All of that is very good, but there's certain points where you would maybe want to create large-scale environments, and having artists sitting there grinding stuff out becomes a problem. Some of you are experiencing this in your 301 projects, where if you only have one artist, you've only got one artist working on your art, and it doesn't scale well. Sometimes it's good to produce programmatic forms of these things. And so that means we can use programs to generate entire worlds. In some ways, we could argue that the universe acts this way. We are a generative phenomena of various underlying processes. That's where I came from. That's where you came from. Maybe we're just procedural content in some god's mind. I'll leave that for the philosophers. But more prosaically, some nice examples of this sort of procedural work can be seen in Dot Krieger and the Sumotori Dreams programs. You see some images there. Have a look at them on YouTube. There should be images of these games. It's from the demo scene more than game scene, even though the Krieger is actually a game. But the thing about these is they are entire environments that fit into a 96K zip. So as far as I'm aware, even the unzipping, what comes out of the zip file is completely procedurally generated. So there's not much content in there, if at all. There are some programs. The program generates itself. So it's like a bootstrap loader in an operating system. And if you have a look, you'll see the audio, The shader programs themselves are generated by the system. That's how they can compress the representation right down. The physics, engines, everything is generated inside the program. And this is sort of like an extreme form of this, but hey, you know, there's some people who've got to work and build games and environments that work in very small footprints. And so procedural content is very handy. Just a caveat, if you decide to download these games, they seem to be infected with viruses. I nearly got caught once doing that. But suffice to say that Krieger and the Sumotori Dreams are just a nice example of procedural content covering everything. So it's something that you should keep in mind. It's a nice technique. It's a whole area of computer graphics. It's also something useful for games and for various applications that you require, particular cities. Cities are a classic approach, whereby because they're sort of square and have fairly regular patterns, you can have some sort of base system which perturbs itself with a bit of noise, and voila, you have a city in front of you. And this is sort of in part driven the idea of the geometry shaders I've talked about, which I've just sort of touched on in this unit. That technology is about procedural content, generating procedural vertex information on the surface of objects. The Xbox has patented hardware to support such techniques. If you feel like it, Google it on the patents site. That was intended because it was they talked about the next gen problem, and it's still an ongoing problem. So let's not call it the next gen problem. It's just a problem of getting enough people to generate enough stuff for games and environments. And so using procedural systems as motivators, using procedural systems is motivated by this need to generate lots of content. So it's a problem to be solved, and there's ongoing research is carried out in this area. You go to computer graphics conferences and engine technology conferences and games conferences, you'll see this sort of stuff emerging. So I concentrate on textures in this unit because there's a lot to cover. I just give you a bit of a deep dive, or sort of deep dive into textures and how that works in a rendering engine. But I also touch on the fact you can affect geometry with these noise functions. And that means it opens up a plethora of possibilities, a plethora of pinatas, a plethora of possibilities. And so, the usual method is, of course, using paint packages and CCDs to capture information in games. And that's the history, typically what has been done. But shader languages have been used for years to generate this surface shading for a long time now. Again, I keep talking about Pixar and RenderMan. A lot of these techniques have emerged from the research done by Cook and Torrance and the other related people in that time. And these things can now be generated in real time. So, the noise functions I show you, you can, if you search the web, you'll find there are real-time noise generation systems out there that you can run on a shader or on a compute shader in your game and use it to affect particle systems and all sorts of things. So, in fact, I think, last night I was trying to repair my demos, which I get to in a minute. I'll just show you what you have to do. The demos are fine. They'll all work. Just there's a couple of things that had to be set up. And I was looking at some Unity noise packages. And interestingly enough, there's a complete package available for 3D Perlin noise. And they give demos that enable you to affect particle systems and generate some really nice flame effects. So all of this is very useful inside a game. So in this case, the procedural texturing is about the generation of diffuse texture values or colors for the surface or volume of an object. And it is procedural as it is described by program code rather than data structures. So this is similar to the idea in AI where you have procedural AI or you have declarative AI. So the techniques here have some declarative process aspects. So it's a mixture. The noise doesn't just work on its own. It's actually a part of having a declarative data structure or deterministic system. And then you add the stochastics together and boom, you end up with something that looks visually pleasing and models what you see in the world. So to move into this, I just cover a couple of basic concepts and some basic procedural shading effects that generate for you these approaches. So first of all, we have to go to the basis of using implicit and explicit procedural techniques. So explicit techniques, the procedure generates the points that make up the object. So you write a script, points come out of the script and build the thing. Implicit works the other way. So the implicit function answers a query about a point in space and returns a value, a color or something like that. So for textures, the implicit approach works better. As I've shown you, texture coordinates are generated by the scan line algorithm as a triangle is turned into fragments. So that means that at that pixel point, you've got texture coordinates. The texture coordinate can then be used to query some function, and it will tell you, I am this color at this point, and you put that into the pixel. And so that's an implicit form. And that means it's suited more to the architecture and the hardware of these systems. So that means as the fragments are generated, the texture coordinates are used to generate the colors, not the other way around. And in fact, in some ways, you can say just textures full stop work that way. But the function is just a simple contiguous array of colors. That's what a texture is. So in this case, you could say that we're adding not an image, we're adding a program. So instead of each texel being an image pixel or a texture pixel, it's actually a link to a program, and the program generates the color, or a function in this case. So here's a really dirt simple example, which is a circle. The common form is an isocurve or an isosurface in 3D. That's how you specify implicit functions. But in this case, to draw the circle, instead of using the standard sort of trigonometric functions that go around using cos and sine, you do it the other way. You say, all right, a texture function is defined as a function f of points p in the texture space. So the pattern is what's known as a level set. Maybe I should highlight that. So it's a level set of f. That is the set of all points at which the function has a particular value. So for a circle of a unit radius, the level set f of p equals to 1 draws for you a circle. Okay? So that means that so in your shaders, as you move through the texture space, you keep handing over the coordinates to the function. And at the point where x squared plus y squared is equal to 1, it returns black. Otherwise, it returns nothing. And that gives you your circle. Sort of magically appears. And basically it's saying, so the color is at that pixel, given that that pixel is equal to some level set, equal to 1. So in this case, x squared plus y squared is equal to r squared, and that's the implicit form of the function. So when r squared is equal to 1, or the unit circle, then this function will return a 1, otherwise it will return 0. And so you get the circle appearing at that distance. And that's really handy for doing a shape. And as you can see, it becomes quite a sort of a trivial process. Give it x and y, or u and v, and it will just simply return the value based upon that. And when x squared plus y squared is equal to 1, then you return the circle. So in this case, the unit circle is an isocurve, and that function has to be well behaved. And hopefully at least C1 continuous. The first derivative is continuous function. Otherwise you get gaps appearing and it ends up being a bit weird. But as I said, think of these implicit functions as special texture corresponding function. Hand it the coordinates and values come back. And you need that in a texture system on a GPU. So where will you have seen these sort of functions? Well, I guarantee you will have seen these sort of functions. Remember the game Spore? I still use it as an example because it was a form of game that heavily needed to do procedural generative effects for the animals in it. Knock yourself out, I think it's still around. You can still get the editor. And the main idea was that these creatures were generated procedurally by you changing parameters, and you got a creature, and then you would put it into the world and fight each other, and blah, blah, blah. And for these, you ended up with these textures, thousands of textures appearing. And my guess is that a lot of the shapes and a lot of the blobbiness of the objects was because they were using implicit functions to generate the shapes. And that means they're parameterizable and you can stretch them and change them, but still generated by a program. So you as the user can sit there generating different shapes for your creatures. And so these also useful, by the way, for modeling fluids, because the blobbiness works quite well. Because it's a field or it's a curve or a surface, that means that you can munch the functions together and pull them apart, and they have sort of liquidy qualities. Some of you who are animators or whatever, you may have played with these sort of curves in blobby modeling. But they're also useful. So they're continuous through a region of modeling space. So they're useful for stone textures, clouds, fogs. So these sort of implicit functions are what generate our effects, and the noise ends up being a form of an implicit function, pre-stored in a texture. So I go through some examples just to begin the process. So you can get things such as wood textures. Instead of hand drawing wood, you generate the wood as a noisy function, or maybe clouds, or maybe marble. You have a look at stone marble, or marble stone. It has a noisy appearance to it. Things such as explosions or flames, all those ideas can be, using noise, implicit functions and noise enable you to generate these shapes. So the whole idea is that because these are procedural functions, and as you can see, it's just a function. It's just f of p equals to 1, and that point is there's going to be x squared plus y squared equal to r squared, in this case 1. Very compact representation. Does not take up much memory. That's how they do Krieger. That's how they do Sumatori dreams. It's a program generating the shapes. So you can compress it right down and then compress it again as an ASCII string. So it's a very compact representation, no fixed resolution, so it's generated in image space because the pixel is the query point. So at that pixel point, tell me what color I am. Great. So that means you can blow these textures up and you don't get magnification. So the only thing you run into is the limited precision of your calculations on a GPU. But they're 128 bits, I think, underlying inside these systems. So therefore, you've got a lot of high precision on GPUs. And so these calculations can be kept, if you use doubles in your shader, you get very high precision effects. There's no need to tile. You just have an unlimited extent. The program generates the texture. So you're not stuffing around with, I've got to make these textures match so they tile. The program generates them. And if it's a continuous function in space, it will just keep on going on generating the shapes and the blobbiness or whatever. Except there's fundamental precision and limits on how big the spaces can be. So I do remember seeing a demo, somebody, those of you who may be into old style science fiction, Larry Niven's Ringworld, famous science fiction, and some students at the University of Washington were doing an assignment where they had to model the ring world, which is, a sort of a synthetic ring around a planet, so it's massive. And the idea was this guy was just going to zoom in onto the area of the ring world and show a map, and zoom in again to come down to a beach or something like that. He ran out of precision in the program. So even though the program was generating the ring and then generating the shapes for the terrain and so forth, I just remember clearly when looking at this example, they said, right, this is the limit of what our hardware can do at the time. This was quite a few years ago, and it just stopped the generation of the shapes. Keep this in mind. It won't matter for anything probably you're doing in this unit and most of your games. But if you start to do some really crazy galactic level scale, you lose precision. And you can parameterize these functions to generate different versions of themselves. And that's their power. So that's what happens here. All these textures are probably parameterized functions from an implicit form, and it just sits there generating nice skins and bumpiness and rough maps and scales, all just based upon a function. You can't do that with an image. You've got to get your artist to generate that again. Here, the program does the job, and it's automated. So disadvantages, hard to model certain textures using implicit functions, especially in non-trivial cases. So noise helps, but it's just tricky. As an artist, as artists, you can sit there and just draw them. That's what humans do. We just look at an image and we replicate it. And there's a big neural net that enables us to do that. To get programs to do it requires another neural net, a programmer, to deal with how to generate those functions. So it's not as easy, but there's lots of examples out there. It can be hard to control the functions. They may go a bit weird, so you can get serendipitous effects, or it can be a mess. Again, you play with the parameters according to sort of normal laws and rules, but this is mathematical modeling, and you have to sort of figure out how to model that. It's also slower because there's a cost to the processing compared to just a straightforward texture lookup. So you've seen what I've shown you with texture maps. That's all very good. In that case, the texture is a LUT, or lookup table. And that's an implicit speed up. So it's faster for the game if the artist generates a tileable texture and the GPU can just blast that onto polygons. However, it's not scalable in variety or in content size because the artist has to keep generating it. But a program can just tweak it and continue to generate different representations. But it's slower. The program costs, it's a shader, it's not an image, so you've got a time versus space trade-off. Aliasing can still be a problem from some of the basic structures that are used to generate them. So, limits on computation prevent you from avoiding aliasing altogether. As I've mentioned before, aliasing is the bane of computer graphics and games, and its realism, or it's just the quality of the effect. Unless, of course, you're doing 8-bit games, then it's part of the fun. But suffice to say, aliasing is still a problem with these functions anyway. But most of the examples I show you scale well, especially things like the wood. So it's a bit of a dark art. Procedural generating colors on the surface of an object is a bit of an art. If you have an understanding of the mathematical functions, it will help you in the process. The main thing is you play with the parameters and learn how they respond. And generally, you use them based upon the input textures, S and T or U and V. But of course, this depends upon how the projection of the texture coordinates works. So you can get distortion at the poles, and that could be a problem. So one of the beautiful things about 3D textures that gets around this, so I'm talking about 3D textures today, which I've alluded to before, is that you avoid some of these distortion problems, especially with spheres. Because as long as the texture coordinate suits, you can then access a 3D texture and just make the thing look like it's carved out of that shape. There's also a layering approach, like I've mentioned with computer graphics and I've talked about with multiple pass shaders. You'll see that there's a blending together of a couple of things in some of these demos to make the shapes and to make the visual appearances. So again, it's like Photoshop, layer upon layer. It's like how artists in oils or watercolors have to layer colors on top of each other. Same thing happens here. So it's like a procedural decomposition. It's like you're writing a program, so you know that your color is made up of base plus a bit of noise plus a certain color ramp. You just sort of pull them all together and put it through. So there's some functions that work in Unity and CG that help you with generating these implicit shapes. So not only just using an actual function such as x squared plus y squared is equal to r squared to make a circle, you can use these to create structures. So for instance, there's the smooth step function, min max x, so returns 0 if x is less than minimum, returns 1 if x is greater than minimum, and returns a smooth Hermite interpolation between 0 and 1 if x is in the range min to max, like this. So smooth step gives you this. So it's like a linear interpolation, but you can also turn things on and off, which I use for brickwork in a minute. Then there's a step function. Actually, no, I don't think we use the step function in the brick because it's a sharp edge. The step function simply, depending upon x, returns the result of x greater than or equal to a particular value. If that's true, 1. If that's false, 0. So once your x goes above c, you have 1. Below c is 0. So you can create steps and you can demarcate zones appropriately. And then there's the clamp function. So returns the minimum if x is less than minimum, returns the maximum if x is greater than maximum. So it just, once you get to the edge of a particular set of texture coordinates, it keeps that value going on for eternity. So remember the clamp function for textures. So if the texture coordinates get to the end of the texture, it just grabs the last pixel and that's the value for the rest of your object. Similar thing here. And so what they enable you to do is to procedurally create simple effects. So here we have the brick demo, which I'll quickly bring up over here. Brick, there it is. Get that. Done. Always that loading process. I should have these preloaded. This sort of wastes your time, but at least you can skip forward. So here's a, this is very simple based upon the texture coordinates. So note it makes it look like you've got a long brick because I've used a cube. But the cool thing about this is that because I'm generating this brick in image space, it does an alias. See? There's no blurring at the edges. There's a little bit of a jaggy there because I haven't turned any aliasing on. But you can see that the edge of the texture just keeps, closer I get in, the sharper it appears or bigger it appears, but there's no blurring. Go back, as you can see, again, there's not too much. Interesting to see what happens if I turn it up and around. Oh, look at that swimming there. Ooh, look at that. Some nice moire effects there. But it still does quite well because it's using the pixel to generate the function. So it doesn't distort as badly as you've seen those image-based checkerboards that I've shown you in the demos. I'll move that up a bit up. So that's just a useful little function, and it's not too hard. It sets it up so that, you know, there's a brick height and a brick width between 0 and 1 and 0 and 1. And it does a test on the texture coordinates for a square shape. And then it modulates the color appropriately. So it just says grout, brick, grout, brick. And that just as the texture coordinates vary from 0 to 1, that repeats over the entire texture. And the color modulation is with reference to these texture coordinates. So you see here, the position ranges in X by 0 to 5.3 and Y from 0 to 13.3. That's a ratio that I actually copied this demo. I'm pretty sure I've got the URL for where I got it from. That's their decision. And so the in position is scaled according to the brick size, and then it offsets the brick by 0.5 in X if the value in Y is greater than 0.5. So effectively it's saying, right, if I've gone past this point here, so if I go above that, then push the next brick to the side by half. So it starts the rendering from that position. So the position gets a half added to it in X, and then we take the fractional component of that, and then we compare the brick with the brick boundary. So the brick boundary is set as being 0.9 of X and 0.85 of Y, and so that's where the step function comes in. So it's saying, comparing my position to the brick boundary, am I on a brick or not? And then if A equals 0 along the mortar regions due to the step function, and A equals 1 in the brick region. So taking the values and multiplying them together, if either one of these is 0, so the brick does a step function in 2 dimensions. So if in X we're on a brick, and then from Y we're on a brick, multiplying them together creates our sort of brick step. And then 1 minus that is the complement. So that A is going to be a step function. And that means that you use the A, you've detected the brick by comparing the position to a brick boundary in X and Y. Then that A is used to modulate the brick color. So if A is equal to 1, you get brick, and that means the mortar color goes to 0, 1 minus A. If you're in the mortar area, so you're not on brick, then you get the mortar color is equal to 1, and the brick color is equal to 0. And then you spit out, so the color is spat out accordingly. So that's how you get this effect. So what we could do, flying by the seat of my pants, yet again, let's play with the amount we're going to add to the brick. I like doing this. I probably have a couple of errors, but that's fine. Offset, because I think this will show you what is going on. Offset is equal to offset is equal to 0.5. That should compile straight away, and then we'll make offset equal to a float down here. You can race ahead on this if you need to. Float off. No, I didn't know how. I'd like to see what happens. Let's see if we got an error. No. Ah! Dumb. What is a dumb error? Dumb transcription error. So, right, that's working fine. There should be a material. Yeah. Offset. Let's see what happens if. Hey, look at that. See? So it's procedurally generated. This is all I wanted to show you, is that I've just played with a variable and I've changed the offset. So it turns into a grid if the offset is equal to 0, and then I can make it, slightly move through. This just shows, hey, procedural texture, blah blah blah. So that means you can play with it in real time, and you get these effects. Artist doesn't have to redraw it. So something to keep in mind. That's a very simple example as an introduction. You could use that as a bump map. You could generate a normal, and that means you can make your brick walls have a bump map within the normal shader. So you could add a function that generates brickwork, and then I'll leave that up to you. You could also generate other shapes this way. So you could generate a filled circle. The easy way is that you assess the function for the texture coordinates, and if it's less than 1, make it the color of the circle. If it's greater than 1, make it no color, or the background color. So that's just some basic shapes. Using those steps and various other forms of functions, you can create just some basic shapes for procedural texturing, and that's sometimes useful. It might be useful for menus. A shader which generates these sort of shapes, squares, circles, ellipses, whatever function you need to maintain that, and it's nice and high quality no matter the scale. So use on your mobile and then put it onto a proper screen or to a large screen, and it should still look really good. That's the benefit of this. Anyway, so irregular textures. So the previous were examples of regular procedural texture synthesis. Say that fast, texture synthesis. So most natural phenomena are not regular. So if you're trying to model things that are skins, such as that spore game I was showing, gases, flames, animal colorations, all those things require an underlying primitive which you haven't learnt yet. You've covered things such as points, lines, polygons, polyhedral meshes. So all those things, the polygons are used as primitives for polyhedral meshes. All those things are great, but they only give regular shapes. What you need in order to model this procedurally then is a form of primitive called noise. Now, noises are generated by pseudo-random or stochastic functions. And they're used in many areas of research because you cannot create real randomness in computers. There's a natural nature, that's the tautology. The nature of the physical systems is they have a very random nature, and that randomness is a mathematical definition that gives you what you see as a randomness, and humans have to process as neural nets. But it also has applications in areas of cryptography and so forth, because that randomness can be used to generate keys and factorize large integers, so forth and so on. The problem is computers can't generate that real randomness. That randomness comes from other sources as part of the physical structure of the universe. So I've seen some very odd cryptographic methods for, having microphones at waterfalls, having antennae just pick up background radiation. So this is an ongoing area of cryptography and mathematical research. I won't touch it here, but just so you get some context. So we try and model that in some way. So let's talk about noise, other than punk and heavy metal concerts. The basic form is white noise. All right. So I think if you run this is actually an animated GIF. There you go. So that's the sort of noise you see on a television when it's not tuned into any station in particular. The system is just sitting there, and no dot in that sequence. So it's actually, think of it, it's a TV, so it's tracing it through the screen. That's a sequence, and no dot in the sequence is correlated with the previous. So that's why you get shapes, because certain things are correlated with each other, and you see that as edges and lines and blobs and so forth. So every number in that stream, every representation of luminance on that display has an equal probability. Okay, so it's just there's no structure. It's noise. And that can be approximated by things such as the pseudo-random number generators you play with, RAND. You probably be interested in what you've done in your programming. Usually they just say, hey, here's a pseudo-random number generator. And again, that's another area of research, generating that. The whole thing is that white noise just comes from background radiation. You don't have these televisions anymore. This is my childhood. You're used to digital systems, and they filter out the noise. Interestingly enough, though, the old analog systems, you could have a noisy image which is still useful. What I find infuriating about digital TV is that if the signal gets noisy, it often just freezes and you can't actually watch it at all. So, fine, digital is much cleaner, but it's less robust to noise from my perspective. So there's no real pattern evident. This is just the background radiation coming from around you. So I mentioned to you when I talked about light, I talked about radiometry and photometry, and talked about how, well, humans seeing the visible spectrum as you walk this earth. Billions of these high energy particles are hitting you, but it's tolerated by the body at a level that we can cope with and live with approximately an 80-year lifespan. It's also why you tend to get cancer in old age. There's a number of reasons, of course, diet, blah, blah, blah. Part of it is just you're bombarded by these radio particles, and they hurt your genetics in your cells. The cells go rogue and you have cancerous growth. I had one removed due to UV radiation hitting my face. So this is a representation of that noise because the antenna on an old school television just picks it up. Other sources of this noise, some of you dudes are into, dudes and dudesses are into guitars. Using guitars, I play with guitar amps. They pick up noise. It's this background noise from various things wandering past. So that's great, but it's not really useful. We don't want white noise. It can never be the same twice. It's just random. So it makes it uncontrollable. So it's not repeatable in a wrap texture coordinate for tiling. It's not a good primitive. You can't control it with parameters because it's a product of random systems. So it's just really a function. It's just the universe spitting at you. So you need a function that takes texture coordinates as input, providing a repeatable pattern. And that noise system needs to respond to it. So pseudo-random numbers are not a solution. Contiguous values are still too decorrelated. Therefore, the values change with viewpoint or instance of the game. So every time you run, it's not particularly correlated. It's also hard to anti-aliasing because those noises, that white noise contains lots of frequencies way above the Nyquist limit. And in fact, white noise has an even probability of all frequencies in whatever domain the function has support in. So, what are we going to do about that? So we need an ideal noise function. This noise is a special form of noise. Part of it is, first of all, it's smoother than white noise. So that makes it blobbier. So it's low pass filtered. That means lumpy, larger frequencies get through. So that means we need a function that has no high frequencies to alias easily and to maintain stability for the irregular textures. So the noise has to have a certain quality. Interestingly enough, this forms a part of modeling noisy functions in Ito calculus. In fact, I get to it in a later slide. So what we need is a form of beautiful noise. Bad dad pun. This is a repeatable pseudo-random function of inputs. It has a known range, so it doesn't exceed the range. It goes between 0 and 1. It's band limited, so it has a maximum frequency of 1, so it just fills it with white, and then the underlying frequencies, it'll fill it with a pattern. The underlying frequencies, back after a break. So with this beautiful noise, it needs to be band limited, max frequency of 1. No obvious periodicities. Weird. But in the end, the idea is it should look random, but it actually isn't. Okay, it's not the sort of thing that is commonly talked about, but effectively it's a fake. The whole idea is that you're making something repeatable and therefore tileable and therefore usable in your game, but it looks random instead as well. These are the things you just have to cope with. It's translation invariant, so the function doesn't change its shape under transformations. It's also isotropic, so it doesn't change with rotation. So remember, anisotropy is physical properties that differ in different directions. This is isotropic, so it's the same in all directions. That means if you rotate the function around, it doesn't change. These things are useful. So how do we create this noise? Where is this coming from? I'm glad you asked. Excuse me, I'm having a cup of coffee. So the Perlin function, Perlin noise is the most common one. It's a form of lattice noise. And they are simple and very efficient to implement. The most popular is Perlin. And the generation begins with one or more uniformly distributed pseudo-random numbers at every point in the texture space, whose coordinates are just integers. So here's a texture. And you fill up the location with a pseudo-random number from rand, 0.5, 0.3, 0.6. So this is just some pseudo-random number generator, which effectively has a white noise nature, but there's some differences about how it gets used and abused before it becomes a Perlin noise. So this is what we call a value noise. And this means that the surface generated here, so it's a limited resolution texture. It's not that big, because the whole idea is that it's going to be repeatable and interpolated between each end to the other end as it wraps around. Now, that was value noise, so you generate a value at each point of the lattice. Gradient noise is where you create a gradient at each location. So instead of it just being a value, the gradient is generated instead at each location. So it means that the noise is limited to being either representing 90 degrees up or 90 degrees down and all values in between. And so that means you end up with the directions, the gradients, representing sort of the change in direction through the surface. And that starts to represent a surface, a lumpy surface of noise. So Perlin noise is gradient noise. So you get more high frequency energy due to changes in direction at each point. So you could have a sudden lift at this point and then the the gradient can go down. And what can happen as well is you can use the previous value noise and the gradient noise and sum them together to generate value gradient noise. So the basis of all these noises are a pseudo-random number generator, a form of white noise, but the idea is that you put them into a grid, and with Perlin you store the gradient, and that is used later on to create a surface, a sort of blobby surface for a base noise. So that forms a basic low resolution integer lattice, and then what you do is you generate a higher resolution by interpolating between the values. So you can imagine that's a very sparse grid, and you smooth it out by generating the points in between. So imagining if the gradient is like this here and this at the next location, you generate a smooth curve between. So that interpolation is a form of a signal filtering. So it becomes that bandwidth, blurred, anti-aliased sort of image, you'll see in a minute, that we can use. And then what you do is to create the 3D noise, to model 3D phenomena, as happens in the real world, then you take a table, a 3D table of those noise lattices and stack them up, and you end up with a 3D form of noise. And the beauty of it is as you interpolate across the images, you also interpolate through the stack, and that's how you get this continuous function through 3D space. So in each case, 2D noise is generated on a plane and then stacked, which is all the 3D texture is. Now, unfortunately, good old CG doesn't have a 3D texture system. It only has a 2D noise function. And the general method of using noise in your shaders is to pre-compute a lookup texture for that noise. So I just searched the net, I found a very simple simplex noise from Google Code here, referenced with STU or UVW coordinates. So that's the function I'm using in my demos. Note it was a DLL, so funnily enough it seems it was targeted at .NET 4.5. Unity now only has .NET 3.5, so I had to stuff around with making them work, but the demos work with this noise function. If you wish, there is a Unity package for noise that is a bit more complex. This is a holdover from when I ran this noise from when I've run the units previously, so I've used it. It's simple. It means the script does not look too complex. But if you wish to, knock yourself out and look up some of these Unity packages with noise, and they give you particle systems that respond to noise and do all sorts of interesting things. Again, I give you simple demos just to make things interesting. In addition, I can't pre-compute these noise functions and store them as a three-dimensional DDS, three-dimensional texture file, which is what I used to do when I taught DirectX in this unit. So that means that the texture demos, I use a script to generate a 3D texture. And then that 3D texture is filled with noise and passed on to the shaders to use in their rendering. So it's a bit of a pain. So it's funny how the good Lord giveth and the good Lord taketh away. And so in the case of using Unity, yes, it's great to use all of Unity's functions, but there's just some things that DirectX had that they haven't bothered to translate into Unity, or just make things a little difficult, and yeah. Anyway, I'm over it. So here's the 3D texture management in C# using the noise generator. You'll see it in the script, but it's really simple. I just generate a texture a 3D texture using the format specified and its size in dimensions. See, in this case, it's only 64 pixels in size, in dimensions. It's interesting. So, but this basis can then be used to create much finer grained details. So it's something worth looking at. So the idea is create the 3D texture. You create quite small textures. We could make them bigger, but I don't think it's going to really change the effect. And putting them through these loops in 3 dimensions, X, Y, and Z. And I use the simplex noise generator function that I've got to put a value inside the texture. And then, lo and behold, that texture, I set the pixels inside the texture. I then apply. One of those things when you're playing around with the guts of textures in Unity, you actually have to make it, load it into the texture by the apply function. So I assume that probably removes a mutex on the memory inside of Unity, because you had to do that sort of stuff with DirectX. And then I pass that texture as a noise sample into the shader. Done. So now we go back to, well, how do we, creating the base noise is all fine. So the lattice is generated at 1 resolution, and then you can generate higher resolutions with smooth properties. So the key issue here is then the interpolation between the values created in the lattice. So I mentioned that here's the 2 gradients, and then you generate a smooth curve matching them, not matching, but are generated by that gradient. So the whole idea is that you want this to be smoother so that you're getting rid of that lumpy sort of white noise effect, and you're getting a noise that starts to look blobbier. So we can't just interpolate linearly because it's too blocky. So just to add another mathematical concept, we use a cubic interpolation scheme. So Catmull-Rom interpolation is often used because what it means is you can specify a gradient at each location, and the line is generated based upon that. So you've done this you don't have to do the maths for this unit. This is just what happens behind the scenes. You specify the gradient at each point, and then it smoothly generates for you the curve from that. So I think, pretty sure Jinlang would have covered splines. They're a basic primitive. And the nice thing about them is, of course, they meet one of the needs that first and second derivative are continuous. And so you can use splines to interpolate anything. In this case, we're interpolating noise and then generating a new smoothed out version of the noise with the gradients being random. That's how it just gets its noisy nature. And that means the transitions are smooth, which is one of the things we wanted with beautiful noise. So the idea is that it's an example of sort of creating a small lookup table and then taking those values as a basis for generating higher resolutions. So you end up with, in some cases, they say 64 control points with the surrounding 27 lattice cells in 3D will generate you a nice, smooth, blobby noise in space. There's other splines that can be used, quadratic, cubic, cubic B-splines are possible. It's neither here nor there. Just get the idea in your head that the gradient is used to generate this smoother function based upon the random gradients inserted. And you'll see that in the images that come about. So once you have that noise, once it's generated and pumped out and put into a lattice, then Perlin noise is used to generate. So once you've got the basis of the noise and you've got this texture in 3D full of that noise, Perlin noise is then parameterized and processed via using scaled versions of each of the textures added together. And so common technique is called 1/Fn noise. which is known to occur often in natural processes. So they got this from monitoring the systems in the natural world, and they have a nature which is known as pink noise, because it has a slightly, if you put it onto the frequencies and visible spectrum, it looks slightly pink. And this noise approximates it by adding suitably scaled harmonics of this basic noise function. So it's a wave, but it's lumpy and all over the place, but it still has this idea of being able to use harmonics of that noise. So that's a new concept here, possibly for you. Those of you who aren't musicians have another understanding of this because you're used to using the harmonic on a guitar. So anyway, you have your base noise, so that's just the texture, and you have your texture coordinates at x. So that can be anything from 1 to 3 dimensions. That dimension is multiplied by a scalar, bi, and divided by another scalar, a. So what happens is, if you increase the value of x, you're going to shrink the texture, making it contain higher frequencies, because you've multiplied the texture coordinates by some factor. And you then divide through to what we'd say, because A is an attenuation factor. So the top part changes the frequency, the bottom part changes how much it contributes. This will become clear when we get to it in a minute. So that's the general form, and you loop through a number of loops, typically 4. Typically you do 4 octaves, or 3 octaves from the base scale. And the idea then is that when you add these components that are scaled and attenuated together, you get certain phenomena appear, or certain visual phenomena that are useful for modeling. This pink noise effect, or the 1 over Fn. And once you add them together, you just get a number back that you can use. It's a noise, and you can use it in your rendering systems. So what do we mean by octaves? Well, I'm glad you asked. So here's a sine wave, sine of x. Sine of 2x has double the frequency because it goes through its goes through all its phases twice in the same amount of time, or the same amount of domain. So here's sine x. If you go sine 2x, you get that effect. So that is a harmonic. So where b is some positive number greater than 1, most commonly it'll be a power of 2 because that creates your harmonics. So for those of you who play guitar, you know that you can strike a note, and then if you gently hit one of the harmonic nodes, you get the octave up, which is twice the frequency. So same concept as music, but it works visually as well, because your noise, now look at this, and then let's look back here at this. See, it's not a sine wave, but the peaks are randomly generated and then interpolated. So you can imagine if you were to take that coordinate system and multiply it by 2, you get a shrunk version of it. Multiply by 4, shrink it again, and so on and so forth. So that's the idea of these adding together the octaves. So typically 2 times gives you the octave. And that the idea is that that gives you a scaled version of that function to add. Now, so n is typically 4, so you know you can go up to 10, but it becomes a disappearing act in the end. It attenuates the noise so much that you don't really get an effect. So usually 4 iterations are enough. You have the A gives you very rough functions, whereas larger values of A, so if you multiply A up, it will attenuate some of the higher frequencies this introduces the technical term fluffiness. Why is this so? Because as you make A large, that bit of noise gets very small in height. So remember, there's the frequency and then there's the amplitude. You divide that by a number, it gets smaller. So there's two things that are happening. You're creating the harmonics or the octaves, and you are generating the, you are attenuating the values as they go through. Now, typically, A and B are some power of 2, right? Because of this octaves idea. Sine x, sine 2x, sine 4x, sine 8x. You've got your 3 octaves based upon the tonic. Let me keep going. But A and B can be arbitrary values, and so the demos I show you, A and B are replaced in some parts by different numbers. They give different effects. Play with them. Some of them have very little effect. Some of the sort of streams of A's and B's that you use. Others will create a really quite striking visual effect upon what you do. So you can modulate that and control it. Just put it in you don't have to just put it in a loop. It can just be a series of additions that you write out. And you can play with what harmonics you attenuate in order to give different effects. So that loop, we're going to see it in one dimension. So the following shows increasing harmonics of one-dimensional Perlin noise along with the sum of the first 8 harmonics at the bottom. So in this case, A and B are both equal to 2. So you're going to get B to the power of n, A to the B to the power of I, A to the power of I, up to n, or n minus 1. And since in practice we only ever add a limited number of harmonics, if we zoom into this function sufficiently, it will become smooth. Think about it here. There's our base noise. That's a noise function generated. Here is the first, so the first iteration of the loop, is this. The second iteration of the loop is the noise at a high frequency, so it's shrunk. It's going through 2 times the cycles compared to the first one. And it's also been scaled down. See, these had quite high peaks. Now they're a lot smaller. Then we do it again. We multiply the base by 4, dividing by 4 again. And we get the peaks are 1/4 the height of the ones here. Do it again with 8. Do it again with 16. And what we see here is this progression from a lumpy looking noise down to what starts to vanishingly become just a mid line that almost looks straight. So if you kept going, 16, 32, yada, 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 you just end up with a straight line. So this has got 5 versions of it. 4 is usually enough. And once you go through that and add them together, this is what the noise starts to look like. Okay, that starts to look like something you'd see on an oscilloscope from a natural system. This one up here is sort of a smooth curve, but down here, some jagged components have been added by taking scale versions of the function and adding them together. And you get this, which is really cool. Now we go to a 2-dimensional version. And this is where hopefully the visuals, the penny will drop. You go, oh, that's what he's doing here. So this is an example why you don't have to sum to large values of n. After the 4th harmonic, the values are less and less than the resolution of a grayscale image, both in terms of spatial resolution and the resolution of the 8-bit grayscale value. So if we look through here, here we go. There's our base noise. Here's the first harmonic, there's the second harmonic, the third harmonic, and then we end up with the fourth harmonic. Not really useful. It just starts to be a grey value that you add to the function. So in the end, you're sort of just adding a number to every value, and you're not changing its resolution. So anyway, here's that smooth noise. See how it's blurred, bandwidth limited, all very nice. We add the scaled and attenuated version, so it's not as bright. It's starting to grow dimmer. And we do it again for 4 times the frequency, 8 times, 16 times. Lo and behold, if we add them together, we get this. And the sum looks a lot like clouds. This fluffiness appears. And so you can start to use that. You can just use it as a sort of form of cloud shader. And then playing with this with various other bits and pieces gives you some nice effects. So this is how the two-dimensional noise is used. And so starting from the tonic and adding the 4 harmonics. So sorry, actually it is adding 4 harmonics I'm not talking about. But that would be 5 times through the loop. The other ones only go to this. So I think you'll find that in most cases there's not much point in even computing that one. See, it's just a grey image. 64 pixels, the frequencies get quite high, so they just don't appear inside the texture. That one still has a bit of dotted speckliness to it, so it's contributing something to the structure of the noise. So A and B are both set to 2, but they can be an infinite number of ways you can play with those harmonics. So if you wanted more of the second harmonic, then the scaling of that can be increased. So if you wanted this to be brighter and contribute more to this shape, then just change A to be a smaller number. Divide through by less, but still scale the function. So it's interesting to just play with this. You can take these, use these as textures if you wish. You've got the source code, you've got the lecture. You grab these, put them in as textures, and just play with the loops as they add together. You can get some really interesting effects. So while the design of a particular effect isn't difficult, it does take some practice to play with this. I guess it's like any art. This is where the art comes in. Now here's a 3D version of the same noise, just to show you how if you play with the scale again, so this one is of a B may be equal to 1, and this one is B equal to 2, the first power of 2. That's about right, 2, maybe 4. You can see there that this translates into 3D. So the noise can be interpolated through the stacks and across the stacks, and you end up with this noise. So it means you can do 3D particle effects, or you can make your objects appear to be carved out of this noisy structure. So the common use of noise is a 3D Perlin noise. It generates a volumetric texture. So that script I showed you back here, remember, in each case, it's a simplex noise. It's not Perlin, but it's close enough that we can just use it to do the same effects. Note, it's got 3 parameters, x, y, z. So generating that first, that interpolated first base noise, you end up, I guess, in 3D with something like this. And that's the base noise that you can use. And it gets around the problem of mapping 2D textures onto 3D objects. Remember I showed you a sphere. You end up with this crimping at the top and the bottom due to the fact the texture coordinates move together based on the basic geometry of the object. Those of you who are artists or deal with the artists in your IGB381 teams, their UV mapping is a long and slow process, because then when you do it over an irregular modeled shape, you get all these problems. So a 3D texture cuts through that. It's just a cloud of noise in 3D space that you use to change the textures wherever they are in 3D space. So, is there anything else there? Okay, so you just don't get that pinching at the poles on a sphere. You have a look at the demos and you'll see that the texture coordinates are fine. So some 3D examples, the classic ones that I'm going to go through, I'm going to do a lava planet, or you can use it for clouds. So you can create planets using these noise functions very easily. In fact, I'll get you to do that in the tutorial. And again, this comes from just this basic idea, Ito diffusion theory. It sort of models noisy systems. So this is a very broad brushstroke. I had a chat with a physicist about this who put me onto this, and I thought, okay, she was seeing what I was doing in my unit, and she thought, oh, that's interesting. You're using Ito diffusion theory to model noisy effects. So the first component is a sort of deterministic, like structured approach, a structured function, and the second part is a Brownian motion addition. And so it sort of generalizes to this. The visual phenomena we want to do, you have a base texture structure, just that sort of thing that's going to be the base structure for the appearance, and then you add the noise. And then that gives you something that looks like a physical system. So I'm going to show you 4 examples, 3 of them with demos. The marble, I don't give you a demo. You can have a play with it yourself. And the whole idea is that you pass just a vector in some dimension, and this noise provides back a scalar. How you use that scalar is the creative part of the process. There's no sort of method, but there is a method. It's that Ito diffusion idea, structure plus noise. But there's just some classic examples here that I show you, just thinking, okay, that's interesting. So you can get there something like a teapot, which is covered with the noise, wood, and it looks like it's carved out of the wood. And all of them play with the 3 parameters: the attenuation A, the harmonic scaling, harmonic creation B, and I is the number of iterations through the loop. And then you just use different color ramps to generate some of these texture effects. And that's basically it. So the first one I'll show you is wood. How much wood can a woodchuck chuck if a woodchuck could chuck wood? I'm so tired. How do I even get through that without stuffing it up? Alrighty. Wood. Assets. Yeah, so yeah, we'll get rid of the brick. Bye-bye brick. Hello wood. Because we like to do carbon sequestration here. These are sustainable shaders. Now, so it starts out, you look at it, it's just a diffuse shader. So there's the simplex noise DLL just inside of it. Just a note, I've made it that it's able to use .NET 4X, and that's done. This is just a handy little tip that you might want to do, but you can Google it and find it anyway. So project settings, player, some of you might have done this already, and you go down through the settings in the player settings, tautological, and you can set it to experimental .NET 4.6 mono background system. And so that will execute higher .NET DLLs. So this is a great way if you've got some .NET DLLs that you need to use. Just make sure that you insert them into your project and check that you've got the right level of .NET compatibility. But it goes without saying, so firing this up. And there we go. It looks like wood. Now we can see here, it's sort of just, it's not that sort of crazy, but you can see it's got this sort of randomness applied to a step function of colors of brown. Thinking about that, it's like the brick, but you add noise to the brick, and you get something that looks a bit more wavy. And so you can play with these parameters, and you get this wood effect. And again, it works in 3D, so it just uses the 3D point on the surface to access the texture, and then lo and behold, that noise is added with some harmonics, and you get this thing that looks like wood. And create planets with it as well. I'm actually looking at this, it reminds me of Jupiter. Again, a turbulent gas. There are better ways to probably model that using Navier-Stokes equations, but lo and behold, here's just a simple wood shader. So how does a wood shader work? So it uses a 3D texture to avoid the swimming in texture coordinate problems I mentioned in lecture 3 or 4 actually. And obtain a scaled and translated object space position on the surface of the object. So I use its point in 3D to access the texture. Interesting enough, compare this to what I was talking about with the normal mapping being done using a TBN space on the surface of the object. That's because we want the normal map to just perturb the surface and follow the surface around. Here, we're creating an object out of a 3D substance, so we use its X, Y, Z coordinates in the space to map it to the texture in 3D, and it looks like it's carved out of that. So we need to get the distance r from the surface to the origin object of origin space, and we scale the values for r to 0 to 1. So that means we've got texture coordinates. We're not going to exceed the texture, and then take that value r and add the noise, so that the accessing of the colors is moved around a bit. And once you've added that noise, use the R value to select a color between dark and light color for wood color gradient. So we've got an orange and a brown in there that we use to do this. So here's the vertex shader. Nothing really crazy there, except we hand over an out, which is the wood position in three-dimensional space, and we scale it and add a small offset. Those things can then be exposed. I guess I can do it. I'll leave it to you, but you could expose that as properties for the shader to change the scale of the wood and where it is in wood space. And then in the pixel shader, that wood position comes in from 3D, the object space, and we use that wood position to access the noise sample. Okay, and what are we doing here? Yep, we divide through, so the wood position is between, I guess between 0 and 1, between 0 and 1. Oh, sorry, well, we're dividing by the texture resolution, so we're basically scaling it according to the texture resolution. Interestingly enough, because it could be negative and positive, we divide by 2 and add 0.5 to change it from a value between 0 and -1 and 1 to between 0 and 1. Then, once that scaled, back after a break, once we have that P wood value, we then get a dot product of the dimensions in Y, Z together and take a square root of it so that we effectively get the radius at that point in Z and Y. So we're doing it in a plane. So the X, so it's a left-handed system. But we want the wood to work in the YZ plane, because that's sort of wood is it layers. You cut it from a tree, and you have rings. The rings are what these gradients are, And so they work on a particular plane around the x-axis. So that means when you look at the wood in this form, you'll see, maybe I'll use the scene, Ross. You'll see that it's a set of rings, and the rings are being perturbed, so it looks like it's being carved through the wood. Okay. Excuse me. So we get R basically using we just scale the value, use the Euclidean hypotenuse calculation in Y and Z, and we get this nicely scaled R, and then we use that R to access the 3D texture again. So we're using that X, oh yeah, so the noise sample has come in. We only need one dimension. Sitting there thinking, what's going on here? Yeah, we're perturbing along one dimension, not 3 dimensions, so we only use the X dimension. Again, scaling it with the resolution of the noise structure, noise texture. And we then play with the values to pass them through to a smooth stepping function. And depending upon where the value R is, we then linearly interpolate between a wood color 1 and a wood color 2. So one of the woods is the orange color, the other wood color is the dark brown. And that gets that sort of, instead of it being a smooth step, we get a change that's irregularly modified through the surface of the wood. And that works out along the x-axis. No, sorry, the x-axis. The x-axis. Left-handed system, x-axis this way. So it moves the wood along there. And lo and behold, you end up with a simple wood shader, which is quite cool. You can play with it. You can make those wood grains very fine. You could make it noisier, which will give a really different appearance. This one is a bit cartoony in appearance, but that's fine. You can use that in some of your games that have a more cel-shaded appearance. Some of the projects I see in 301, I see these effects available that could be, used because you're using a much more cartoony style. Then, let's kill that. Let's go to the next one. Lava. Actually, the flame one is probably my favorite. Sorry to slurp. It's a little hot. There we go. All right. Now, in the previous wood, the wood was made out of those steps, but they were noised up a bit, so they moved up and down to create this sort of woody effect. Here, we're actually using a bark texture instead of Beethoven, to represent our I don't want to use that one. Stop it. You can see that there. So this texture is then used as a basis for our lava, and then we add some noise along a color grading. So the wood color grading was just 2 colors. This one we vary between a number of colors. So once you fire it up, we have that. So it's not a hard one again. It's just, but it just, you can see the underlying bark maybe through there. It sort of forms the basis. And lo and behold, there are these sort of lumpy things that move in and out of color spaces and look like it's flowing lava, which I think is really cool. one of my second favourite effects. And of course you can quickly drop this on some of your games where you have lava needed. So it just looks like flowing lava in time. So how do we do that? So this is a variation of a marble shader that resembles the appearance of Io or the sun. Uses a different color scheme to create the hot appearance. So marble just needs blue and white in the example. Here we go color ramp from yellow to red to black to represent the temperatures of the gas or liquid involved. So there's a bit of science, but it's sort of a real gross approximation. And again, we use a 3D texture to avoid the swimming and texture coordinate problem. So if we look, I'll run it again. If we look here, you shouldn't see, it's crossed. I don't think there's any poles ever. See, it's undistorted. It's just moving across the surface. I'm not seeing any location of particular weirdness occurring. Just you're getting these blobs moving through space on the surface of the object, and it just looks like a flowing lava. So this noise is different. So in the previous wood, we just used a basic noise. So again, you can do what you like with the noise. And all it did was just move the dark and light bands around. Here, we're going to sum for 4 octaves by multiplying the texture coordinates by a factor. And we attenuate the higher frequencies by dividing through by a power of 4.17. Okay, so that gives it a smoother, lava-y appearance. We also use a sample from the bark texture with this noise. And then we blend the noise samples with yellow color and add 2 red values. So we've got 2 colors, but it goes through to dark, so we end up with, I guess, a 3rd color coming through. So the first lava is this bright yellow orangey, and then the second color is just a darker red. And then in our pixel shader, so again, we're using the world coordinates on the surface to get access to that. We also just use time to multiply by about 300ths, and added to the world position to just move the lava through the surface. Remember, you can translate and transform textures. So in the for loop here, so this for loop is that basic function. We sample the noise with the texture coordinates at some power f, scaling it. So this is where we get the finer details because we're multiplying the texture coordinates by f. And then we divide it through by divide by 2 and add 0.4, playing with the values. And then the other key component is we then take that noise and attenuate it by some power of 4.17 f. So remember I said A and B don't have to be 2. You can use arbitrary values. So here, in this example, the 4 octaves of noise, a for loop of 4, takes the volume and the volumetric texture at different frequencies. So as you're multiplying the coordinates by f, they get smaller and smaller, and then you're adding them together with a scaled version of that noise. So it's divided by f, and f just goes up by 4.17 every loop, so it's a power series. No, it's not a power series, it's just a sequence, it's just a power of 4.17. And then we sample from the noisy bark and add that texture and multiply it by the lava 1 color and add to it a bit of lava color 2. So the bright yellow gets a darker red added to it, and that becomes the output color. So that's what you get with this. So you can see it's not really a black, I guess it heads towards a black, but on further examination it really is a deep red. So it's an example, a classic example of creating lava-y sort of effects. Final one is my favorite, it's fire. So if we have a look here again, I get the flame. Is this where I sing the cheap tricks on? No. I hear the screams from here. So looking at that, we see, I just apply it to a cube because, you know, hey, why not? And we see here what looks like flames. And that's all, the noise is added to the texture to make it appear flame-like. So it's a different usage of the noise again, not to sort of interpolate between colors per se, but it uses a texture to sort of draw it out and make it flamey. Again, same thing, but this is our base texture. So instead of it being bark, which needed to be noisy because we're doing lava, this one, it's a base flame, which sort of makes sense because a flame is a sort of jet of gas, I guess, from the wick and the wax, or gas system, whatever. And the flame is a gradient of color, going from orange up to bright yellow. I guess if you'd be picky, you could put a bit of blue at the top. And lo and behold, this is the basis for the whole setup. And then noise is added through time along the y-axis to create that effect. And it's not a difficult or complex thing. It's just that gradient made symmetric, and then noise is added through it, and you just end up with these powerful effects occurring. So going back to here, how does that noise create? So sorry, there's the base texture. So you can see there that the base flame texture is just applied through the cube, and that's it without any noise added. Add the noise and get the flame. So, what's happening? Another variation of thing using noise. And now, so the base image, adding noise. This perturbs the image using the usual scale and translated noise to give a flame appearance. And you animate by translating the effect like a vortex in Y. So we just use time again to move. So remember all that little simple animated texture I showed in the other lecture. This is a more the same it's just a simple translation, but it's added noise to it to make it flame-like. So you add the noise in time along the Y direction to spread flames up with a noisy perturbation. So you've got a delta, a change, and it just pushes it around according to that noise. So there's no real effect needed in X and Y, X and Z, which is interesting, isn't it? So the effect moves up. The world coordinates ends up being like a rotating flame texture around the y-axis to shade the object. So think of it in principle as a column of flame, and the noise goes up in Y, and that's all. So moving down here, so some tweakables. So the noise scale, animation, -1 in Y. Why is it -1? Because it's in texture space. So you've got to go up, which, since the origin is the top left, you actually want to go -1 in Y. The flame color, is just an addition of a small amount of white to it, scale and translate for the flame on the object. So there's some tweakables. Noise strength, time scale of 1, and a noise frequency. So this one uses, and this one it's funny, I use explicitly the underscore time, the Unity shader lab function that I've mentioned before. So I'm just using its Y value, not the Y going up, but just its time. So it's time in seconds, I think, in Y. And I modulate by the value 10 in order to avoid large texture coordinates. So it wraps around at 10. And what we do is we get the world position in space, and we multiply by some sort of the noise scale, the noise frequency, so just how big you want the flame and how it's played out, and the time plus the time value times time scale and noise animation. So this is going to go up in Y by going along the negative Y axis in texture space, just to confuse you. And then the flame position is just the world position times flame scale plus a flame translate, so you can move it in 3D space. So, moving through, this is the pixel shader. So it's all done in a pixel shader. So the radial distance in the XZ plane is just the length of the vector XZ. And then the direction, the UV coordinates in Y are just the in flame position dot Y. So when we go back to the vertex shader, the flame position has the flame translate added, and the flame animate added, and the flame noise animation goes in negative 0.1. So that means the noise position moves up through the noise space along the y-axis in a negative manner. Now, going back here, I've got a turbulence function. So the effect is attenuated with distance from the center divided by uv dot x. So along y, we add this turbulent value for the texture. So that comes from a noise map we've handed in. So every script, I should show you that every one of these shaders generates its noise using that script I talked about. So every one of them does that. Have a look at them. And we take that noise position, uses the texture coordinate into the noise map, and then we just multiply by a factor. These sort of factors are just used to, attenuate its strength, and then we divide through by x to get our direction y, and then that is used to access the flame texture. So the first thing we do is we take the texture coordinates and perturb them in y using the noise function, the turbulence function, and then that UV coordinate just accesses the base flame texture, this one here. Once you add that to y, you get the flame effect. Now, that turbulence function is this loop. So again, here's the loop, and this one is a classic noise function of a power of 2, sampled 4 times. So we end up with the bass tonic plus 3 octaves, P by power 2, P by 2, P by 4, which is 2 to the power 2, P by 8, which is 2 to the power 3, dividing through by a half, a quarter, an eighth, and a 16th. And that gives us, remember, if we do the powers of 2, we get this fluffy effect here. Okay, so this sort of noise works well for this form of flame. Anyway, there are other ways you can perturb it, play around with it. There are variables there you can play with. And lo and behold, so that's an unrolled loop. So instead of doing a for loop, it just does it 4 times, adding the noise 3D function in. So fairly straightforward, really. It's just that loop every time, and then it sums it together and passes back the sum of the noise. And that's used to generate a perturbed noise value in Y. And then that's then used to multiply by some flame color as another tweakable. So you can make it an orange flame or a red flame or something like that. So that's probably my favorite. It looks really stunning. The last one that I'll just go through the theory for, and then I cover terrains. So this one's about marble material. It's formed by turbulent mixing of various bands of rock. So it's a molten effect, and then it cools down, and you end up with the fact that the bands of different minerals just end up distorted with each other and you end up with marble. So this creates solid marble texturing with distinct veins. So we use the volume texture for noise generation to generate this. So in 3D, imagine in 3D, the noise I showed you sort of starts to become those distorted veins. So some parameters, there's an ambient, diffuse and specular material color and coefficients, usual stuff, contributing light color and global ambient. And then there's a noise amplitude and frequency, and then there's a vein turbulence, sharpness and frequency. So that's the one that mixes the colors together. So in previous versions, we've mixed wood together, we've mixed lava colors together, and we've mixed flame colors together. This one, the flame was a perturbed texture. This one, we're mixing blue and white together to get these veins. So the steps for marble: generate a noise value, determine the vein turbulence using noise. So take that noise and put it through a turbulence function. Then blend the vein color with the base solid material, the blue and the white. And then shade using a diffusely reflected light and add specular highlights. And you've got marble. Note that we need that specular component because it's shiny. You might also, as an exercise, could add environment map. Think about it. So actually, if you think about it, the example I give you of the environment map is in the Sistine Chapel with marble floors, and you can see the reflections. So there's another example there where you could start to generate some really nice looking effects on the object. So it uses that volumetric noise function. So remember, it's just the base 3D noise. So that's our noise function. And then this turns it into a signed noise by multiplying by 2 and minusing 1. So, and that texture position is used to interpolate the noise. So the noise is just the noise applied to the elephant example. Then, to get the vein turbulence, we accumulate those multiple octaves of noise with a magnitude decrease along the frequency. So you can see that shape there. Again, it's like flame. That looks like a frozen flame. And you end up with a visual impression of turbulent fluid flow. So the highest frequencies are faded out, so we get this more lumpy sort of appearance, more flowy. And then we blend between the vein color and the base color using that turbulence coefficient. So imagine that, yeah, you're mixing these two colors together, but it's a noisy mixture. So at some locations, you get a lot of white. At some locations, you get a lot of blue. And as you can see there, that's the turbulence. So I'll make it, no, doesn't make it bigger. There can use this. Just blow it up a bit. So that's the noise function there, and it's going to control the mixing of the two colors. So where it's a high value, you're going to get a lot of white. When it's a low value, you're going to get a lot of blue. Just using a step function. Sorry, a lerp, sorry. So to mix the colors, there's an A and a B and a float blend factor. And so that means that the two colors are blended together by that blend factor. The blend factor is the noise. So I think you'll find, so there's the mix. What happens is, instead of just getting a smooth mixture between the A and B, the vein color and the base color, you use turbulence to mix them together, and that gives you the marble. And then if you wish, you create, here's just Ka ambient, diffuse values. That's just a diffuse lighting value. So there's nothing crazy about that. You just use the demos that I've given you if you wish to create it. And then you might add a specular component to it. So here's our turbulently multiplied together blue and white, and then add the specular, and the specular just makes it look shiny. You might want to add an environment map to that in order to create a marble effect. So once again, and by the way, sorry, that turbulence value, that turbulence factor, you would get from the same turbulence function as used in the flame. It's just the same function. And you play around with the noise map values. So, you could use the turbulence function in an include file if you wish for the shader. So that's marble. Cool. Create marble looking things in your game. And of course you can modify the turbulence and make it swim if you like. That would be interesting. So with general rules, there are variation on a theme. So I've mentioned that. Take a base image, flame, bark, etc. Sum together a number of octaves of the noise via texture coordinates. And at the same time, weight the sum of these octaves to enhance or suppress the presence of lower or higher frequencies. That's parameter A. So sum of octaves, parameter B. So I probably should just say parameter B, just so it's clear. Weight the sum of these octaves, hence parameter A. So, and that will give you these nice effects, just as a general rule. So it's something you can play with. The next one I want to show as an example sort of goes in a different direction. You don't necessarily have to just do the colors of the geometry. You can use the noise to model geometry itself. So the image on the next slide is just the noise function used in the displacement map demonstration demo. Here. So what I've done, literally what I've done, instead of using the grid that I showed in the demo before, I just saved this as an image and then used that to displace a high resolution just flat quad, and lo and behold I end up with this terrain-like structure. So that's straightforward. You just use that and it automatically looks like a terrain. So it starts to open up the possibilities of using noise to generate terrains using geometry. Keep this in mind. And there are various methods for that use fractals or subdivision surfaces. Again, you could disappear down a dark hole of theory in this space. I just want to throw this at you to say, hey, you could change the geometry and make something look really interesting. So, since these procedural methods generate textures, the same effect can be applied as bump maps for water. So the noise, you see water and it's noisy, there's just splashy effects and whatever, you can use that. On parallax maps, the noise information ends up being a height field for use by other algorithms. Or if you want to, you can create sketchy line drawings Think about it. When you use a pen, or sorry, a pencil, it's often a noise to the lines that you draw as you sketch. So you can model that using this. So you could perturb a line drawing using these sort of noise functions. Or you can make it control animation so it looks realistic. You've been, well, probably not watching me, following the slides, but if you watch me, I fidget. There's just movements that happen. But also, you know, idle animations, people often just sit there moving around, and it's a noise function. It's generated because our muscles get tired or we get sore feet and we start moving around. Now, it's not, let's say, it's not that our whole body turns to noise because we're constrained. Remember, this is noise on top of structure. So our body is the structure. It can only move certain ways. We don't wibble wobble like water. But you can then add noise to the joint movements and you get these very realistic looking effects. Something to think about. So, that's the end of the lecture for today on procedural generation in games and game engines. Thank you very much.